Hi everyone, my name is Yao Li. I'm a PhD student from the University of Pennsylvania. Today, I'm going to talk to you about embracing a mechanized formalization gap, a way of interactive reasoning for Haskell code at scale. This is a joint work with Anton, Joachim, and Stephanie. So here is how the story starts. We are a group of people who love the Haskell programming language. In the meantime, we also like to use formal verification tools to reason about programs. In particular, we like to use the interactive theorem provers, such as coq. Well, wouldn't it be nice if we can use our favorite interactive theorem prover to reason about our favorite programming language? Well, we would like to do that. But first, we will need a way to transform a program written in Haskell into a program written in coq. Now, how do we do that? Traditionally, there are two ways of doing that. The first one is manually extracting a model, or in other words, to manually translate the program in one programming language to another programming language. Now, the original program can be very big, so it is usually very hard to translate the program while retaining all the details of the original program. So usually, a model for verification would only capture the essence of the original program while ignoring many other details. As a consequence, this can exhibit a large formalization gap between the model and the original program. Alternatively, one can also try to mechanically translate the program written in one programming language to another one. Now, because this is a mechanical translation that does not involve human effort, this can usually retain all the details of the original program, and therefore exhibit a very small formalization gap. However, one have to first construct a complete translation mechanic from these two programming languages, and this can sometimes be very hard, especially so when the two programming languages has very different set of features. For example, coq would require all the programs to be total, while Haskell does not have that restriction. And another problem with mechanical translation is that because the translated program would contain all the details of the original program, even those that are loosely relevant or even irrelevant to the properties you want to reason about, this would bring some extra burden for formal verification. Now, we have discussed two different approaches of translating a program, namely the model approach and the mechanical translation approach. I want to discuss one thing that they have in common, that is the formalization gap. Even though they have the differences that one having a large formalization gap and the other one has a small formalization gap, the formalization gap exists in both of these approaches, and it is not something that we can eliminate. What does this mean? A formalization gap is the difference between the original program and the program we actually reason about. What this means is that no matter how hard we try, because of the existence of the formalization gap, we are always verifying something different from the program we actually want to reason about. Therefore, the formalization gap has always been perceived as a weakness of formal verification, something that keeps formal verification from perfection. However, in this talk, I want to convince you otherwise. I want to show you that at least in the field of formal verification, being imperfect is okay, and being imperfect has its own advantages. In particular, the formalization gap should not just be considered as a bug. It can be a feature that you can make use of to your own advantages. And this point of view comes from our own experience of applying interactive theorem provers to Haskell. We have developed a tool that automatically translates Haskell programs to coq programs, and we name our tool hs-to-coq, unsurprisingly. And in the past, we have applied this tool to verify some existing Haskell programs. In particular, we have applied that to Haskell's containers library, which contains certain Haskell data structures, such as data.map and data.intermap, etc. And we are eager to search for some bigger target for verification. And what would be a better target than GHC itself? Now, when we started our project Haskell-to-coq, we were aiming for a tool of mechanical translation. However, our view changes dramatically during our verification of GHC. To understand why this happened, we need to examine some of the characteristics of GHC. First, it is a large program. It is one of the largest open source programs written in Haskell that is available to us. And it is a mature project. Its first prototype was developed some 3 decades ago, and it is still under active development. And it has a very heavy focus on performance while being developed. And this is one thing that contrasts from many other verified programs, that it is not written with verification in mind. What does this mean for verification? Well, let's look at some numbers. Let's take GHC 8.4.3 as an example, which is the GHC we try to reason about. It contains 464 Haskell modules and over 182,000 lines of code. That does not include comment or blank lines, and that is a lot of Haskell code. In the past, when we try to verify the containers library, we have on average 8.5 lines of coq proof per line of Haskell code. And if we apply that estimation here, that means over 1,500,000 lines of coq proofs for this entire project. And that's a lot of coq proofs. And that is actually one order of magnitude higher than the current version of CompCert, another verified compiler. Therefore, it is practically impossible to verify the entire GHC. So instead of doing that, we ask ourselves this question: can we just verify some properties of part of GHC? Let's look at the GHC compilation pipeline here. Can we focus our attention on the core-to-core optimizations of the entire compilation pipeline? Or more specifically, can we just focus our attention on these 2 properties, namely, the term substitution preserves the scope of variables, and the extensification preserves the scope of variables as well as the join point invariant. Now, it is not important to understand what exactly this property means to understand this talk, and we choose these 2 properties mostly based on the familiarities and interest of our group members. The important thing to remember is that these properties are what the GHC implementation is expected to satisfy. And these modules in combination contain just about 500 lines of Haskell code, and that should be pretty manageable. Well, if only things are that simple, remember when we started this project, we were trying to build hs-to-coq as a mechanical translation tool. However, in order to just verify some properties of part of GHC, we have to face 3 challenges with a mechanical translation. First, even though the modules we focus on are very small, they have a lot of dependencies. Therefore, we have to have a way to select these modules out of the huge dependency graph. Second, mechanical translation would contain a lot of details of GHC, even those that are less relevant to the properties we care about. Therefore, we have to have some way to simplify the translation until the formal verification of the property we care about is manageable. And third, coq and Haskell are different programming languages, and we have to have a way to reconcile the discrepancy of the 2 different programming languages. We have figured out a way to overcome all these 3 challenges. That is, by introducing a formalization gap. But it's not just any formalization gap. Is a mechanized formalization gap. Let's look at an example. So here I'm showing you some code. On the left-hand side, we have some Haskell code. It's some data type definitions about the core intermediate language in GHC. Here is the expression data type. Now, you do not need to understand all these constructors, but I do want to direct your attention to the tick constructor here. This is something important during development, because this tick constructor requires some profiling information. But this is not as useful during formal verification. In fact, since we are only dealing with term substitution and extensification, we would like to ignore this constructor in our formal reasoning. In the meantime, we would like to retain as much details as possible of the expression data type in our translation. So what we would do is doing a mechanical translation of this expression data type, while intentionally ignore the tick constructor. And the way we do this is by explicitly instructing our translation tool to introduce a formalization gap. In hs-to-coq, this instruction is called an edit. And in this particular case, it's a skip constructor edit. This edit will tell hs-to-coq to ignore all the declarations of this constructor and all the pattern matching clauses of this constructor, but just that. In this way, we are not arbitrarily tampering with the code after translation. Instead, we are giving a set of documented instructions to our translation tool to introduce the differences in a mechanical way. And this is why we call this approach with a mechanized formalization gap. In our work, we have used edits extensively to reason about GHC code that is otherwise impossible to formally reason about. Now, I have prepared you with one simple example of use of edits. Now we can move on to something more drastic. Recall that one of the two modules we want to reason about is exitify. Normally, in order to reason that, we also need to formally reason about its dependencies. For example, exitify depends on var module, and var module in its turn depends on the name module, and name module in its turn depends on module, and module also depends on unique. And I can go on. And remember that exitify does not just rely on one module, it relies on many other modules. And in this way, all these modules formed a very intricate dependency graph in GHC. Start our formal reasoning from the root of the dependency graph would mean a lot of work. And many of these modules are not even relevant to the properties we want to reason about. So we don't just want to reason about all of them. To reason about is the exitify module. So we have used the skip module edit to skip a lot of these modules. However, not all the modules are skippable. Some modules are used in some of the important modules, but their particular implementation is not so relevant to the properties we want to prove about. So we need a way to abstract these modules. Well, but how do we abstract over something in the translated code? Well, the answer may sound a bit dangerous when you first hear about that. That is, by using axiomatization. Let's take an example. Recall that we are trying to reason about term substitution, so we do not want to be distracted by coercion variables or type variables, and because reasoning about them is extremely complicated. So we would like a way to abstract over these data types. So we just make these data types axioms in coq. This does apparently introduce more axioms to the proof system. However, we argue that this is fine because these axioms do not break the soundness of the proof system, because types are apparently inhabitable. Furthermore, when it comes to the usage of coercion or type variables, we would like to simplify our reasoning by stating that there's no free variable in any coercions or types. One way of doing that is to also state these properties as axioms. However, in our work, we have found there's another type of edit which is more proper here. That is the rewrite edit. What it does is simply that every time a function call that tries to collect the free variables from a coercion or type, it will simply replace the function call with empty set. And you might ask, with a good reason, that how is this edit more proper? Especially considering that this program now has a clear semantic difference with what GHC implementation actually does. And you are right that now we are reasoning about a program that has a clear semantic difference with the original program. But just because of simplification of a less relevant part of the code, we are able to get to the properties we actually care about quickly. And that is far better than wasting a lot of time before getting to these properties, or worse, not being able to verify these properties. And that is why the formalization gap should really be considered as a feature here. Yes, we are now getting something less accurate here because of this formalization gap. But it also makes it far easier for us to get something. And that's, as I will show in this talk later, that something can be quite useful. However, we do have to be aware that this sort of behavior have some potential dangers, and we have to watch out. Let's take an example. Let's look at the undefined function from Haskell. We cannot just translate this function into coq. Well, maybe we can axiomize it. Well, that would be a terrible idea, because this function undefined would return any value of an arbitrary type A. That means we can use this function to prove false and break the soundness of our proof system. And then we can use that to prove anything we want. And we cannot do that. Even though we have extensive use of the formalization gap in our work, we are very careful about what we do, and we try very hard to avoid situations like this or other things that would break the soundness of our proof system. Now let me give you a better sense of the scale of our work and the size for our formalization gap by giving you some statistics. we have identified the Haskell modules that are relevant to the properties we want to reason about in GHC. And these modules consist of over 22,000 lines of Haskell code. And we use hs-to-coq to mechanically translate these Haskell modules. And this translation is guided by over 1,700 lines of edits. This results in over 18,000 lines of translated coq code. The line of code is smaller than the original Haskell code because of our use of edits, including some simplifications or even axiomatization. And improving and reasoning about the properties we care about, we have produced over 13,000 lines of theorems and proofs. Let me explain a little bit more about these numbers here. Some of you might still remember an 8.5 ratio I've mentioned earlier between the coq proofs and original Haskell code. The ratio here seems to be far less than 8.5. The reason is that the original 8.5 ratio talks about the complete specification of the original Haskell module and the proofs for it, while here we are only reasoning about some properties of the part of the code. Now, I also want to mention a bit about the number for the edits here. First, by looking at these numbers, you will notice that there is a large formalization gap in our work. But in the meantime, because these edits are guided by explicit instructions and they are mechanized, we have actually a documented formalization gap that other people can check to see what exactly the difference are there between the original program and the program we're reasoning about. But all these numbers do not tell us one thing, and that is also the thing that you would have perfectly reasonable reason to be skeptical about. That is this really useful? I'm happy to report that we have a positive answer for this question. First, in our work on the term substitution, we are able to identify an error in the specification that is recorded in the comment of the code, which the implementation is expected to follow. And in the expectation part, we have been able to identify a very subtle bug. Both of these errors we have reported to GHC developers and got fixed in later versions of GHC. And that is the result of our current work. In the future, there are several directions that can be explored with this approach. The first direction is a proof maintenance study, when the original code gets updated. And the second is a comprehensive study of the mechanized formalization gap. For example, trying to identify what is a good set of edits. And my personal favorite is the third direction, that a more drastic use of the formalization gap. For example, can we replace the data types from the original program with some other data types so we can have a better reasoning about certain programs? And finally, I would like to end this talk with our most important point, that is, the formalization gap can be a feature that you can make use of for your own advantage, and you can consider using that for verifying existing Haskell programs. That is the end of my talk.